Welcome to ECE 761 Robotics, lecture number 14, Robots in Contact with the Environment. Now the problem we want to look at here is what happens when a robot comes in contact with a surface. Say I want to polish the floor or mop the floor. I want to push back and forth with a constant force on the tip in the Y direction. What used to be a 2-degree of freedom robot is now 1 degree of freedom. By constraining the tip position y2 equals 0, I eliminate 1 degree freedom so that now when I specify the tip position, I now specify all the joint angles, giving you just a 1 degree freedom robot. So the question is, how do you simulate such a system? Well, this is going to look at one solution. One way to do that is to redo the dynamics. What used to be a 2 degree freedom system is now only 1 degree of freedom. If I specify y2, that specifies theta 1 and theta 2. And doing some trigonometry, the way it works out is that theta 2 is now minus 2 times theta 1. So really just have 1 degree freedom. One way to figure out the dynamics is to redo the Lagrangians. I have the position of the shoulder, position of the tip, but I have the constraint that theta 2 is minus 2 times theta 1. So putting everything in terms of theta 1 gives you the kinetic energy, the potential energy. So this is now the Lagrangian. The torque on the first joint then is the full derivative of the partial derivative of L with respect to theta 1 dot minus the partial of L with respect to theta 1. Partial with respect to theta 1 dot will be this function, partial with respect to theta 1. Now take the full derivative, and I have the torque as a function of the acceleration in theta 1. That also comes with a constraint that theta 2 is minus 2 theta 1, theta 2 dot is minus 2 theta 1 dot, theta 2 acceleration is minus 2 theta 1 double prime. The torque on the second joint was just as it was before, but I now know theta 2, theta 1, albeit theta 2 is a function of theta 1. Substituting, I get the torque on the second joint is also a function of theta 1. Now, if I rotate 90 degrees, so that 0 is defining the x-axis, I get the following for the torque 2. So that is the joint torques if there's no tip force. If there is a tip force, then added to the previous calculations, the tip forces convert to the torques through the Jacobian transpose. This is one way to do it. Note that it's kind of a painful way. When I come in contact with a surface, the dynamics completely change. In free space, I have 2 degrees of freedom. I have torque 1, torque 2. As soon as I come in contact with the environment, I now have 1 degree of freedom. I have to reformulate the entire dynamics. That's just kind of one way to model it. That's also kind of counterintuitive. If you take your hand and move it around in free space, and then suddenly come in contact with a surface like a table, your dynamics don't really change that much. The control law that you use to control your hand doesn't change that much. If you do this sort of formulation, however, then I have to completely come up with a new set of dynamics, new control law. Everything changes as soon as I come in contact with a surface. If I want to control the x position, what I could do is use a control law to control the desired acceleration in the xy direction, use the Jacobian to convert these to desired accelerations, then convert the accelerations to joint torques through the inverse dynamics. Then to control the tip forces, I can just use the Jacobian as well. But I'll do that through an integrator. One of the problems you have is that torques and forces are directly related by the Jacobian. It's a static relationship. If I want to be able to adjust the torques to control the force, what I'll do is I'll throw an integrator in series. That way, if the tip force is too small, I'll slowly increase the torques based upon the error. That's an integrator. So let's get into tip forces and Jacobians. if I have a robot in contact with a wall, I can apply a tip force. Suppose I am in contact with the environment. How do I model the tip forces? Well, the answer to that is, again, the Jacobian. The force in the xy coordinates, actually, power, energy equals energy. Power is force times velocity, which is torque times angular velocity. If I throw Jacobian in there, Jacobian times tip velocity is joint velocities. That gives me the relationship. The force is torque times Jacobian, or the way we've been writing it, the force is Jacobian transpose times the torques as column vectors. So Jacobian transpose relates forces to torques. For example, if I have a robot in this position, 0.5 radians, 0.6 radians, and the torques are 1 newton meter, 2 newton meters, the tip force is -4 in the x direction, -2 in the y direction. So the tip force is this direction. If I have a tip force, I pull this up, the resulting torques are going to be 4.8 newton meters on this guy, also being pulled up. And this guy's actually going to be negative. Pushing down, try to compensate for the x, torque being 0. So Jacobians relate tip forces to joint torques. If I want to maintain a force on the robot, say I'm leaning against the wall, want to maintain the torque, I'll then use the Jacobian. I'll take the error in the forces, convert that to the error in the torques through the Jacobian, and then integrate to get my desired torque. This is a static system, so the gain could be anything you want. The response time could be almost anything you want. Basically what you do is you push against the wall, then lean harder and harder until I have my desired torque, or desired tip force. And I can make the gain, how quickly I adjust, as large as I want. Basically, tip forces can be applied very, very quickly. In simulation, I can do that. It's just an open loop integrator. If I want a tip force of 1 newton, 2 newtons, xy, then what I'll do is just integrate the error, and very quickly I'll have the x being 1 newton, y being 2 newtons. If I change y without changing x, very quickly I change y without changing x. So that's kind of the idea behind tip forces. If you have a robot in contact with the environment, one way to model it is to completely change the dynamics, or completely change the formulation. But that makes life rather hard. Once I'm in contact with the environment, I can maintain tip forces extremely quickly. Basically, current is torque, torque is force. So just by maintaining the current, I can make the torques or forces whatever I want. That's kind of the idea behind tip forces. Again, once I'm in contact with the environment, I can maintain forces using a slightly different technique. There's no homework for this week. It's basically the joint torques and forces are very similar to, or related to the tip. Try it again. Tip forces are related to joint torques through the Jacobian. Tip velocities are related to joint velocities through the Jacobian. Jacobian appears all the time. That's lecture number 14 for ECE 761 Robotics.